Hi, my name is Chen. Welcome to Research Design and Analysis Seminar Series. Today, I'm going to talk about statistic analysis of COVID-19 data. The COVID-19 data is usually measured in case counts over some time sequence in geographic regions, such as countries, states, counties, and cities. In this seminar, I will use the state and the county data from United States as my examples. The basic method can be extended to other geographic regions, such as other countries. I will use the open source R and the SaTScan statistic package as my basic tool for doing data analysis. I will start by looking at how to access and set up data file to display COVID-19 cases and deaths in time sequence. To use time series array model to fit the time series model and to make prediction from the data. Then I will display COVID-19 data in maps and to test the spatial autocorrelations. To employ spatial regression models for both state and county data, and then to build a simple spatial time Bayesian model of COVID-19 cases and deaths. At the end, I will use Kulldorff spatial scan statistic to detect clusterings of COVID-19 cases and deaths can choose for covariates. Let's begin with COVID-19 data. Here is the website to download COVID-19 data for all 51 states. Start from the beginning back to March 2020 and up to March 7th, 2021. I use an R program to download data and to import data into R for analysis. Here is data view in R. COVID-19 data can be arranged by state and by dates. Different states have different starting time. For example, state of Alaska, AK, start recording of the COVID-19 data on March 6, 2020. And Massachusetts start recording COVID-19 data on March 18, 2020. And state of the New York start on March 15, 2020. This table shows COVID-19 cases and death counts for 51 states as March 7 of 2021. It includes cumulative cases and deaths as March 7th and the new cases and deaths on March 7th. The largest number of the cases and deaths is state of California. However, when we take the population size into consideration, North Dakota has the most confirmed COVID-19 cases. That is about 13% of population, while Hawaii has the fewest. That is about 2% of population. Here is COVID-19 data for Massachusetts only. In a time sequence start from March 18 back to 2020. And here, for example, on March 18, 2020, the cumulative cases was 156. And then there was 73 new cases on March 19. So the cumulative cases on March 19 is 156 plus 73 equal to 229. Similarly, the cumulative deaths on March 18 was 2, plus 1 new death on March 19. So the cumulative deaths on March 19 was 3. This table is COVID-19 data for New York State in a time sequence start from March 15, 2020. This graphic shows time sequence chart of case for states Massachusetts and New York. For state Massachusetts, the maximum daily cases was on January 1st, 2021. It was 9,003 counts. That was about 20.5 per 100,000 population. While the state New York, the maximum count was on January 15th, 2021. It was about 19,942. That was about 34.6 per 100,000 population. This is a similar chart, but for the death count. The maximum number of the daily deaths in Massachusetts was 252 on April 29, 2020, while the maximum number of the daily deaths in state New York was 951 on May 7, 2020. The slope is negative. There are decreasing trends of the COVID-19 cases since 2021. This chart compares the trends of daily cases with the daily deaths. The peak period are not the same. The peak period of the daily cases and the daily deaths are not the same. The higher number of the cases was in January 2021, while the higher number of the deaths was in April 2020. The correlation between cases and deaths is positive and is about 0.40. Here is the comparison of the daily cases and deaths for New England's 6 states. The purple curve is for state of Connecticut. It is on the top of all 4 graphics. Even for the graphics of the deaths in 100,000 population, Massachusetts is in red color. The case per 100 population, the case per 100,000 population is lower compared to the state of Rhode Island. This figure is the comparison of the cases and the cumulative cases for states of Massachusetts and New York with smooth curve. This figure is the comparison of the deaths and the cumulative deaths for the state of Massachusetts and New York with smooth curve. Okay, now this is the time series Riemann model for Massachusetts in 2020 with an autoregressive of order 5, first difference, and a moving average of order 1. The estimate parameter of drift is the slope of the time trend. It is negative trend and nearly significant. We use the data as of March 7, 2021, and to predict the next 7 days with 95% of confidence interval. Now here is the residual check for the preview Riemann model. The ACF of the residuals are within 0.2 bands, which means 0, minus 0.2, and 0 plus 2. The autocorrelation is quite small. And then the box Nanjing test for the residuals is not significant, which means there's no significance autocorrelation of the residuals. However, the stationary test was rejected by using the ADF test, but was not rejected by using CAPS test with the p-value equal to 0.1. The p-value of the stationary test by using ADF has to be smaller in order to not reject the null hypothesis of the stationary. Now, the residuals look like normal distributed since the normality test is not rejected. Now, this is the output for the ARIMA model for COVID-19 death count in Massachusetts in 2021. We used the data as of the March 7, 2021 to predict the next 7 days with 95% of the confidence interval. The residuals looks close to normal distribution in a bell shape of the histogram. The normality test was not rejected. The null hypothesis of stationary was not rejected based on both ADF and CAPS test. There is no significant auto-regression present for the residuals based on box-Lorentz test, which means this model fit quite well. Now, since outcome measurement, such as COVID-19 cases and death counts, are arranged in geographic regions, such as states and counties, we can view counts and death counts on maps and test if there is significance of the spatial autocorrelation. Since all places are related, but nearby places are often more strongly related than distant places, the assumption of independency of observations for the general linear model may not valid. We can use marine eye test to test if there is any spatial autocorrelations. Marine eye test for spatial autocorrelation is a general test. It has high power against a range of spatial alternatives. However, it does not provide much help in terms of which alternative spatial model will be more appreciated. According to Estin 1995 article and 2008 book, we can use the range multiplier test to choose a spatial model between spatial error models and spatial lag models. Both LM tests are significant. Then we will choose higher value of the LM test in robust version with lower p-values. Now, this is the map plot of the COVID-19 deaths per 10,000 population on the right, and just the death count on the left. Okay. The marine eye test for the COVID-19 deaths per 100,000 was significant, with the test statistic is of 2.868 and the smaller p-value that is smaller than 5%, which indicate there is spatial autocorrelation present for the COVID-19 deaths per 10,000 10,000 population. This plot shows the COVID-19 cases of the 51 states on the map. The marine eye test statistic is significant if the COVID-19 cases is in the percent of the population. The p-value again is small, which shows there is significant of the spatial autocorrelation. As we know, the general linear model is based on one of the assumptions of the independency of the residuals. For spatial data, things closer in space tend to be more similar than things further apart. The assumption of the independencies of residuals is violated if the assumption is violated, the estimate of the variance are biased, underestimation of standard error. Some covariates may look significant when in fact they are not. We'll show this in an example later when we present the output based on the spatial model. Spatial error model takes spatial dependencies into consideration by using a spatial weighted matrix and estimate spatial coefficients rho, which to include the spatial lag dependent variable is an additional predictor. For the COVID-19 data, we first run the general linear models, and we use Marine's eye tests to test if there is significances of the spatial autocorrelation of the residuals based on the general linear models. Here, the marine eye test statistic are significant with smaller p-values, less than 5%. Okay, which means the assumption of the general linear model were not valid. Okay, so in that case, we need to choose a spatial model. And we use the LM robust test to select a spatial lag model for both best model and the case model. Okay, since the when we run the LM test, okay, both the LM test for lag model and the spatial error model were significant, and then we have to go to the robust version to pick up the higher value of the test statistic and the lower value of the lower p-values, which is the spatial lag model for both deaths per 10,000 population and the case percent population here. Now, for the COVID-19 death model here, the unemployment rate is significant, which is estimated as 0.799, significant at 5% level. Okay. And it is positively related to the death of the COVID-19. For the COVID-19 case model, the median household income is significant, and it is estimated as minus 0.059, which means for every $1,000 increase in the median household income, the case percent is expected to be decreased by 0.059. That is significant. And it is negative relationship between median household income and COVID-19 cases. Residuals based on both lag model were not significant. Those two map plot are the residual plot. Okay. Residuals have been saved based on the spatial lag model. And then we also use the marine ice test to test if there is spatial autocorrelation of the residuals. The null hypotheses have not been rejected, which means this model the spatial lag model fits quite well in comparison of the AIC values. Okay. The AIC value for spatial lag model are much smaller compared to the AICs based on the general linear model here. Okay. Now, spatial regression model can be extended to the spatial time Bayesian model with the assumption of the flat priors. Okay. For this model, we take a sequence of the outcome in time sequence into consideration. Compared to the previous model, we only use the 1 day of the outcomes, okay, 8th of March 7th. But here we take a sequence of the outcome measurements is the COVID-19 cases and the death count into consideration by using a spatial time Bayesian model here with flat prior. Okay. Now let's take a look at this outcome. And for the cases model, and again, similar to the previous model here, the median household income was significant based on the 95% of the confidence interval, and it is also negative related to the case, which means the higher median household income, lower COVID-19 cases present. Now for the death count model here, and both median household income and unemployment rate was significant based on 95% of the confidence interval. Again, the household income is negative and related to the death count. Higher income, lower death count. And the unemployment rate is positive associated with death count. Higher unemployment rate and higher death count. Now here is the trace and the density of the estimated parameters based on deep samplings. The trace is stable and the distribution of the parameters are close to a normal density curve. Now we extend our method to COVID-19 county data with additional covariates. In addition to the median household income and the unemployment rate, for this county data, we take the percentage of the age 65 years old and the percentage of rural areas is of additional covariates into consideration. The average percentage of the age over 65 is about 19.3%, and then the average percentage of rural area is about 58.6%. This map shows the COVID-19 cases present in percent of the population as of the March 13, 2021. The visual inspection shows that there could be spatial autocorrelation since the higher values, which is dark color, are clustered together, while the lower value of the cases, which is light color, are also clustered together. Okay, like northeastern with the lower number of the cases in percent of the population here. Okay, now the marine eye test statistic is significant, which shows there is spatial autocorrelation present. This map shows COVID-19 cases percent of population this is COVID-19 death counts as of March 13, shows the deaths per 10,000 population in a county map. The visual inspection shows that the spatial autocorrelation may be present. Marine eye test is significant, with higher test statistic value is 37 and the very lower p-values. P-value, actually the p-value is close to 0. Okay. Now just examine this map. We can see that those dark color are clustering together. Okay, those dark color here are those counties with higher death count per 10,000 population. Okay, and those light color are for those counties with lower death count per 10,000 population here. Okay, now we also run the general linear model first for the county data for both cases and deaths. The residuals, okay, the residuals based on both general linear model were significant based on marine's eye test. So, and we also use the LM test to choose the spatial error model in compare to the spatial lag model. This spatial error model has the higher value of the test statistics of the LM robust test with the smaller p-value, according to Eslin's article of the 1995. So we use this criteria to choose the spatial error model here. The spatial autocorrelation in spatial error model are estimated as the 0.597 for the death model and as the 0.669 for the case model. Both are significant. The AICs for the spatial error model here compare to the general linear model are much smaller. And then the residuals of the spatial error model were significant. The marine eye test of the spatial error model were also significant. I will guess this is due to the large number of the counties. We have the county number over 3,000. For the death model here, the median household income is estimated to be -2. That means for every 1,000 increase in median household income, the expected death rate is decreased by 0.22 per 10,000 population. The unemployment rate is estimated as 0.296. That is also significant and is positive related to the death count. The percentage of the age over 65, okay, is also significant and is positive, which means with the higher percentage of the population with age over 65, and then there is higher death rate. The percentage of rural area is also significant, with the estimate of the coefficient -0.014 that is negative associated with the death count. Okay. Higher percentage of the rural area, lower death count. Now let's examine the COVID-19 case model here. The median household income is estimated as -0.066. For 1,000 increase in the median household income, the expected case is decreased by 0.066% of the population. Okay. Now here, the percentage of the age over 65 is significant, but is negatively related to the case of the COVID-19. I can think of a reason for that. The older people is more likely to stay away from crowds to prevent the COVID-19 spread. The same reason that the percent of the rural area is significant, but negatively related to the COVID-19 cases. Okay. Now next, we're going to use a spatial scan statistic developed by Kulldorff in 1997's article to identify the geographic clusterings using the moving window on the study regions. The idea of Kulldorff spatial scan statistic is to move windows over study region and to calculate the likelihood function for each window and compare windows, pick up a window with the highest likelihood function as the most likely cluster. For the count data is the COVID-19 cases and the death count. We used to choose the Poisson distribution. Kulldorff spatial scan statistic assumes that the counts, okay, denoted by C, are generated by a Poisson distribution with mean proportional to the lambda times the population, which is P here. Okay, here the lambda is the disease rate. Okay, for example, it's COVID-19's rate or the death rate, or the expected ratio of the counts to the population. Both lambda and the lambda still can be estimated by using the maximum likelihood. Under the null hypothesis, the disease rate lambda is equal inside and outside of the study region. Now, under the alternative hypothesis, the lambda is higher inside of the region, which is inside of the moving window, than the outside of region. Given a region with uniform disease rate lambda inside of the region and also uniform disease rate outside of the study region or moving window, and the test statistics is the likelihood ratio test. Actually, it's log likelihood ratio test. The highest value present is the most likely cluster region. We compute the score function of generalized log likelihood ratio test and find the region with the maximum value of these scores. And we've used a free software SaTScan for this calculation. Okay, so for our COVID-19 data here, and we do that we use SaTScan for both COVID-19 cases and for both COVID-19 cases and the death counts. The input variables are the observed count, expected values, population, and the location. The output will be shown in both text and the maps with the most clustering region. Actually, the output in the text, it lists all the clustering regions, start from the most clustering region and the next clustering region here. Now, here is the output for the COVID-19 cases of the clustering region. The most cluster region, so-called the cluster 1, is the counties in Florida. The relative risk is 4.96. The log likelihood ratio test statistic is this big number with significant p-values, And then for all the study region in cluster 1, then this is the number of the cases and then the expected count. The next cluster region, which is in this area, include counties in Arizona, California, and Nevada. The relative risk is about 4 times. And the log likelihood ratio test scores here is the next higher value. That is also significant with the p-value close to 0. Now here is the study of the clustering for the COVID-19 deaths adjusted for the income and unemployment rate. The most clustering region, which include counties in Connecticut, state of New York, New Jersey, and Pennsylvania. Okay. The relative risk is about 2.5. Okay. Now here is the log likelihood ratio test score with significant p-value. Now the next clustering region is the counties in the Florida here with the even higher relative risk, which is 4.7. However, the clusters are ordered by the log likelihood ratio test statistic, not by relative risk. Okay. So even this relative risk is higher for the Florida region, but it's still the second clustering region here. And all those circles are other significant clustering regions here in the map. Okay. include number of the counties. Okay. These are the references we used for this study. Thank you.